Hello grade 10, how are you today? I hope you're doing fine. So in this video I'm going to talk about what's magnetism, okay? There's going to be two videos about magnetism. This one I'm going to focus on magnetism itself, and the other one I'm going to talk about electromagnetism. Magnetism was discovered in Greece 600 years before Christ era in the region of named Magnesia. That's why it received this name. Okay, so this is just a map. It's a small region in Greece. So here it was the discovery. What they observed? They observed an ore with the ability to attract small objects, and they named this ore magnetite. Okay, that's why it received the name after the region, Magnesia. Magnet is an object that can attract each other and usually contains iron, nickel, or cobalt. Okay. So iron is very common. We can see this almost everywhere. Nickel is usually used to make coins, and cobalt is usually in industry to make equipment and a lot of things. Magnetism describes all the phenomena caused by magnets. So if you have these three materials, iron, nickel, or cobalt, you have some magnetic property. And the magnetism is what describes the phenomena that this magnet creates. To understand what's a magnet, we need to understand that inside each magnet we have some regions that we call domains. These domains act like tiny magnets with its own north and south pole. So observe these two, this picture here. Each region here is a domain. And as you can see, the arrows represent the direction. Okay, so here we can see the direction are not aligned at all. So we say that this one is a non-magnetized arrow because the domains are not aligned. And observe this one. If you can see this one, the directions, they are all aligned. So we call it magnetized iron because the domains are aligned. If you have a more aligned domain, the more aligned I have, the stronger is my magnetic power. Okay, so more aligned these domains here, stronger is my magnetic power. All magnets have a north ticking and a south ticking pole. The north pole of a magnet, by convention, is the end that naturally seeks the Earth magnetic pole near the geographic North Pole. So the North Pole of a magnet has the direction of the North Pole, of the geographic North Pole. And the other end is directed by the South Pole. Here we have a compass. This compass is equipped with a freely moving needle. So here's the needle, freely moving. This needle rapidly locates the magnet North Pole. So it always points to the north. And because it always points to the north, I can locate all the four cardinal points, so south, east, and west. Okay, because the compass, it guides us by showing us the North Pole, so we can know by which direction is all the others. It's the same as we have been talking about charges. Here, opposite magnet poles attract each other, and like magnet poles repel each other. So it's the same principle. If they are different, so north and south pole, they attract each other. But different ones, for example, north and north, they repel, or south and south, they also repel. So the same repel each other, and the opposite attract each other. Magnet force is the force of attraction or repulsion between magnets. They can act over a distance through a magnetic field. And what's magnetic field? Field is the area or of space in which the magnetic force of a magnet acts on another magnet, being represented by magnetic field lines. So here we have, for example, this magnet here, and it has its own two poles, north and south, and these arrows represent my magnetic field, okay? And there is a convention for us to write down these lines. The convention is that the lines always goes away from the North Pole. So we always go out from the North Pole to the south. So always from north to the south. This is the convention, okay? And toward the South Pole. So from the north toward the south. From the north toward the south. So you always need to write like that. This is the convention to represent magnetic field. And the lines are closest to one another near the poles. So near the poles is where I have the closest lines because they are areas of the greatest magnetic intensity. So here in the poles, always from north to south that I need to write. But here in the close to the poles, I have the biggest magnetic force or magnetic intensity because they are closer, okay? The closer they are, the more intense it is, even though they are repelling, okay? So for example here, they are repelling each other, but still they are closer than in the other, if you compare from the other regions, for example. How do I magnetize objects? So as I already told you, magnetism is a natural magnet, so the magnetite has already magnetic properties itself, okay? But we can make some artificial magnets by exposing them to another magnetic field. So even though objects is not magnetized, I can make them to be magnetized by exposing them to another magnetic field. So here's an example. How do I create this magnet? I need to align the domain. Remember, I need to align. So for example, in the left, I have some domains inside an object that are not aligned. So I don't have an electric field. But if I put some magnetic field closer to it, for example, here the red arrow is showing me an external electric field, okay, magnetic field. What it's doing? It's directing, it's attracting or repelling, depends, this electric field from these objects, and it's aligning. So all the electrical domains will be aligned. So I create a magnetized object by aligning the domains. So here on the left, my domains are randomly aligned, so I don't have a magnetic field or it's very weak. And in the right, I have my domains aligned because of the external field. So I have created an object that is now magnetized. And we call ferromagnetic substance all the substance that has the ability to acquire magnetic properties. So not all objects can acquire magnetic properties, but some can. So those who can acquire magnetic properties, we call them ferromagnetic substance. We can also do the opposite. We can also do demagnetization. Demagnetization is the process of reducing or removing the magnetism of a ferromagnetic material. Okay, so instead of creating, I'm removing or reducing. How do I do that? So usually it's by impact. Okay, for example, hammering or dropping an object. For example, here you can see the picture. I can create strong and sharp blow. When I do that, my domain became not aligned anymore, so I don't have so strong magnetic properties. Okay, we can also do it by heating to a high temperature. So if I heat this object here at a high temperature, I can demagnetize this object, okay? Sometimes not completely, it depends on the object itself, but we can reduce its property of its magnetic property. And another concept I want you guys to know is magnetic remanence. Remanence is the ability of a material to acquire and to conserve magnetic properties. So some objects can acquire and conserve magnetic properties very well, and some don't. Okay, those who doesn't conserve, we call them temporary magnets. They easily acquire, but they also easily lose magnetic properties. Okay, so it's easy for them to acquire, but also to lose. So they are temporary magnets. The domains are easily aligned, but also easily misaligned. It means that even though they are magnetized now, if I do something, they are gonna, if I disalign the domains, they will not be magnetized anymore. Okay, and it's easy to destabilize the alignment of the domains. So we call them low magnetic remanence because they have weak ability to keep the magnetic properties. So for example, here I have a needle, and the needle is not a strong magnet, but if I rub it with a strong magnet, it's gonna acquire some magnetism property. And then if I put them close, for example, to a paper clips, a metal paper clips, it's gonna attract, okay? But after some time, they're gonna lose this property. So they are temporary magnets. For some time, they can be magnet, but just after a few times, they cannot anymore. And on the other hand, the permanent magnets. They are hard to acquire, so it's hard to have the magnet properties, but also is hard to lose. So once they get the magnet properties, they don't lose very easy. They are difficult to align or misalign the domain. So it's hard to align or misalign the domains, but once it's aligned, they don't lose very easily. And we call them high magnetic remanences. Usually is the magnetic bars like this one. They have permanent magnets. Okay, they are permanent magnets because it's really hard for them to lose the domains. So we need, for example, a huge impact, just like I told you before, for them to lose. Okay, and after some time, they may align again and acquire again. But here, for example, for the needle, they acquire very fast, but they also lose very fast. Okay, guys, so this one is really short. It's just an introduction, okay? And I hope you enjoy. And thanks so much for watching.